Hello friends, in the last video as we have seen about how selection sort works and what is selection sort. In this video I am going to explain you about the complete analysis of selection sort. Selection sort, suppose an array A, as we know that the definition of selection sort, as it is very simple, we are very much aware we have to select a particular uh, uh, element from the list, and after that the sorting algorithm is an in-place comparison based algorithm in which the list is divided into two different parts. As we know, we have discussed it in the last video as well. It is in-place comparison based algorithm in which the list is divided into two parts, the sorted part and is on the left hand side, and the unsorted part is at the right end. Initially the sorted part is empty and unsorted part is the whole entire remaining list, in which now we can suppose that an array A with n elements, for example say n elements, is in the memory. Selection sort works as follows. As we know, first find the smallest element in the list and put it in the first position. That's a very simple task. First you have to put any smallest element into the from the list and put it in the first position. Then find the second smallest element in the list, put it in the second position. Third smallest element in the list, third position, and so on, unless and until the whole list may get sorted. Look at the example where A1, 2, 3, 4, 5, 6, 7, 8, these are the elements, K1 and K first position as well as the fourth position. What I have identified, what we are going to find, see 77, 33, 44, 11, 88, 22, 66 and 55, these are the given elements. Look at the second row, whereas the values from the second row, 77, 33, 44, 11. In that given list, there are 8 different elements. From that 8 different elements, the most smallest element is 11. Compare that 11 with, or swap that 11 with the first position, that is 77. Definitely 11 will be at 77 position and 77 will be at 11th position. That means A4 is swapped with A1. Ultimately we can say that K is equal to 1, LOC is equal to 4. Now 11, there is no any need to swap or change or disturb the position of the element number 11. Now the second smallest element in the list is 22. We have select that element, swap it with the second position value, that is 33 is already there, swap it with 22, 22 will be at 33's position and 33 will be at 22's position. Definitely it goes over there. Now the list will become like this: 11, 22, 44, 77, 88, 33, 66 and 55. Now the third smallest element in the given list is 33. Select that element 33, swap it with the third position, because its appropriate position is position number 3 in the sorted list. So there is already one member present named at 44. Swap the element number 33 with 44, and in the fourth iteration or fourth pass you may get 3 elements sorted: 11, 22, 33. Next element is 44, swap it with 77, then 88, then 66 and so on, like that. At the end of the list you may definitely find your complete sorted list of elements by applying or by using, say, selection sort. How selection sort works, this is the best example. In the first pass, I am now explaining it with the help of these lines. Find the location of the smallest element in the list, A1, A2, A3 up to AN, then interchange a location with A1. That's why then and only then the A1 will become the sorted, cause A1 will be the very first position in your sorted list. Find the location of the smallest element in the sub list, that is from A2, A3 up to AN. Do not disturb A1. A2 onwards you have to find the smallest element and swap it. Then A2 may get its appropriate position. Pass 3, A3 onwards we have to find it, or we have to find the smallest element from A3 onwards till AN. Interchange a location, interchange ALOC, that is location, and A3. Then A1 is A1, A2 and A3 is sorted since A2 is less than or equal to A3. We have to do unless and until n number of elements. Find the location of the smallest element in the sublist AN minus 1 and AN. Then interchange a location and AN minus 1. Then A1, A2 up to AN is sorted since AN minus 1 is less than or equal to AN. Ultimately, you may get the complete sorted list after n minus 1 passes. Another example, a cards example, where initial configuration is like this: search all cards and find the largest. Whatever the largest, you have to keep it at last or at first, we can say. The swap is performed in 3 different steps. First, your largest element is say ace, will kept first, then king, then queen, then the J, and then the 10. Ultimately, this whole swapping is performed in 3 different steps. Among the remaining cards, the king is the largest one. Firstly, I have sorted the very largest element, that is say ace, that kept it on the left hand side, which is sorted, and that's why I have given them the green color. In the remaining 4 cards, nothing is sorted, and I found it that the king is at the largest position among the unsorted array, unsorted list of cards. But the algorithm may perform some empty operations. Swap it with itself in place, cause the king is already in its appropriate position. No need to no need to swap. Definitely, now we came to know that there are 2 elements which are sorted, A and K. Again, 3 different elements or 3 different cards are still not sorted. Now, after looking at the remaining cards, the queen is the largest one. It will remain in its place cause it is already there in its appropriate position. But the algorithm may perform some empty operations, that is swap that element with itself in place, or in other words we can say that no need to swap, it's already in its appropriate position. In the next step, ace, king and queen are in sorted order. Now there are 2 different cards are still remaining, that is 10 and jack. Among the remaining card, the jack is the largest. If we compare it with the 2, jack is the largest. It will remain in place, but in algorithm it may perform some empty operation. Swap it with itself or swap it with 10. Definitely it may swap it with 10, and you may get the next sorted order, that is ace, king, queen, jack and 10. This is the final sorted order, or this is the final sorted list among the given cards. And after that we are down at the last card, because there is only 1 card is remaining, and because we know that it is smaller than all the rest, so we did not need to do anything or any algorithm or any swapping with that 10, else we with it. Hey, this is why the algorithm goes up to less than n minus 1. Ultimately, I can say that there are 5 different cards, and the steps required to sort or comparison required to sort are 5 minus 1, that is 4. All cards are sorted now. With respect to C, if I say that selection sort include stdlib.h, define n6, int main, int a is equal to, say, this particular example. Again, the same algorithm is there for selection sort. And with respect to time and space complexity, I can say that analysis of this selection sort, outer loop executes n minus 1 time, inner loop executes n minus I minus 1 comparison. So the whole comparison may get that worst case, average case and best case time complexity is order of n to the power 2. The worst case occurs if the array is already sorted in descending order. Best case occurs is equal to order of n to the power 2, that is n square. Average case also order of n square. In selection sort in place of sorting algorithm, so it takes constant order of 1 space, or the time space complexity is denotes with order of 1 itself. Thank you for patience hearing.